Okay, your next assignment's due a week from today, on the 16th. That's the second of 3 assignments that we have from Chapter 4. So problems 40, 41, 46, 49. We're going to go over a few more ideas from Euler's equation today, just expanding on what we started with last time. Remember that in the previous class we said this is the beginning of Euler's equation, and the purpose of Euler's equation is to predict changes in pressure that's due to a local acceleration. So when we were using the hydrostatic equation, we were saying that fluids were not moving. And so we need some way to account for fluids that are moving with respect to position, which is convective acceleration, which is non-uniform flow. And sometimes we're going to have fluids that are moving with respect to time, and that's local acceleration. And that's what Euler's equation does, is it helps us to predict changes in pressure that arise when there is an acceleration other than gravitational. So we say that the change in piezometric pressure between points that are distance L apart is a function of the density of the fluid and the acceleration that the fluid is experiencing. And the minus sign here is reflective of the fact that the pressure increases in the opposite direction that the acceleration is occurring. So when we actually apply that to problem solving, what we're going to do is pick 2 points. We're going to usually be given the pressure at one location and want to find the pressure at another. Or it may be that we're solving for some pressure difference. So to apply it between 2 points, we have to assume a linear variation in pressure between those 2 points. And so these partial differentials become just a change in the piezometric pressure over some incremental distance. And so our definition for what's location 1 and what's location 2, remember, the convention is that if we're solving for some acceleration in the x direction, then 2 is going to be the spot that has more distance in that x direction. And 1 would be the point that's further to the left, or having less x. If the acceleration is vertical, then we'll use number 2 will be the one that has the most vertical elevation, and number 1 is the spot that has the least vertical elevation. Now here's a word of warning. We can only apply Euler's equation for one acceleration at a time. And so if an object is experiencing acceleration in more than one direction, then you have to do Euler's equation in different steps. It has to be sequential. So first you would go the L direction that you're going to be applying this force for whatever direction there's acceleration. And I'll show you an example today of how if we're experiencing acceleration in 2 different directions, how we have to first find the effect of the acceleration in one direction and then find the effect of acceleration in the other. So it'll be a cumulative distance. But you wouldn't solve for 2 accelerations in a single step, and you'll see what I mean by that. So when we solved this example in class last time, what we had was an acceleration to the left. Since it's slowing down, that means it was moving to the right and it's slowing down, so the acceleration is to the left. And what we saw was more pressure at A than there was at T, because the pressure at A is higher. Remember, the pressure increases in the opposite direction of acceleration. So if it was accelerating to the left, that means that the pressure increases as we go in the rightward direction. And the highest pressure was down here at B, because that's below, that's as far down as we can get, and then it's as far to the right as we can get inside of that tank. So what we did was we solved Euler's equation, and we were able to go from point T all the way to point B, even though there was both a horizontal distance and a vertical distance. We can solve that in a single step because there was only one acceleration. It was just horizontally accelerating. If it had been vertically accelerated, then we would have to do one direction and then the other. But here, we were able to go straight from T to B, and Euler's equation handled both the hydrostatic effect and the effect of this additional acceleration over and above gravitational. Okay, so let's apply Euler's equation to flow through a pipe. What if water is flowing through a pipe and we want to know the pressure gradient needed to accelerate water in a horizontal pipe at 6 meters per second squared? So remember, it can be a little bit confusing, but we can have pressure changes in a pipe that are accounting for this acceleration over time. So Euler's equation, we're going to apply it for a pipe that's horizontally oriented like this. And we've got location A and location B, and it's asking for the pressure gradient. What it means by that is what's the change in pressure per unit distance between the 2 points. See, delta P divided by delta L would be what they mean by pressure gradient. So let's get that practice of expanding Euler's equation. Now, A versus B, which one, if this is a horizontal acceleration, which is location 2 and which is location 1? Remember, horizontal acceleration, our convention is whatever is further to the right is going to be location 2. So that means that location 2 is going to be B, and location 1 is A. And so when we expand out Euler's equation, it's going to be P plus gamma Z at location B minus P plus gamma Z at location A is equal to minus delta X, density of the fluid, acceleration in the X direction. Okay, now the givens here is that it's water in this fluid, and so the density is going to be 1,000 kilograms per cubic meter. It's given that the acceleration is, it's accelerated 6 meters per second. So that is A sub x is 6 meters per second squared. And we're going to let the delta x be 1 meter. So we're going to rearrange this for delta p divided by delta x. Okay, now the other thing we need to recognize is that if we expand out Euler's equation, that's going to be the pressure at B plus gamma ZB minus the pressure at A minus gamma ZA is equal to negative delta X density acceleration in X. The two elevations are the same. ZA equals ZB because it's a horizontal pipe. So we can cancel out that term, the ZA and the ZB term. So it's just PB minus PA. And that is delta P. So in other words, delta P is equal to minus delta X density acceleration in X. And so the pressure gradient is going to be delta P divided by delta X. So that's minus density acceleration in X. So minus 1,000 kilograms per cubic meter multiplied by 6 meters per second squared. Okay. So if we look at the units there, it's going to be minus 6,000 kilogram meter per second squared per cubic meter. Kilogram meter per second squared is a Newton. So it's In other words, these units are newtons per meter cubed. And a Pascal is a Newton per meter squared. So it is minus 6,000 Pascal per meter is what we have. So pressure gradient, it's asking, what is the pressure gradient needed to accelerate it? So the pressure gradient is going to be delta P per L. So the units there should be pascals will be the delta P units. The delta L is going to be meters. So minus 6,000 pascals per meter. So if we want this to accelerate to the right at 6 meters per second squared, and A and B are a meter apart, then what we should measure is that the pressure at B is 6,000 pascals less than the pressure at A. So the negative sign here means that in the direction of flow, the pressure would be decreasing 6,000 pascals for every meter that we go towards the right. So that's one application of Euler's equation, and I think you may have a homework problem that is similar to this, where you're looking at pressure differences. Okay, any questions about this one? All right, now I think this is probably the most important example we're going to work today, and I have a handout for you on this one, because what I'd like you to do is, after I kind of talk you through some of the basics, work with your classmates on this, because we've got both an unknown pressure difference and an unknown distance. And so I'm going to talk you through what you need to do to solve it. And I would really prefer it if you solve it with another classmate. So it's better to scoot together with somebody else so that you can help them and they can help you. So, all right, we've got a tank full of mercury. So that's the first thing we need to be aware of is, in Euler's equation, the density is going to be 13.56 times the normal density of water. Okay, that's the first thing. It's accelerating in two directions simultaneously. It's accelerating to the right at 15 meters per second, and it's accelerating downward at 12.5 meters per second. Okay, so before we start crunching any numbers, let's just talk qualitatively. What do we expect? If it's accelerating to the right, how is the pressure going to be different at H compared to G? Higher where? Higher at G. Okay, that's good. Yeah, so we know we're given the pressure at G and we're given the pressure at H, and it matches what we expect. So we know those pressures, but what we don't know is how far apart they are. So that's going to be the calculated thing, is we're going to use Euler's equation to tell us how far apart those two are. So in other words, here in the full expanded version of Euler's equation, the unknown is going to be delta x. Okay, now let's think vertically. It's accelerating downward at 12.5 meters per second squared. What's g? How many meters per second squared is g? 9.81. Okay, so if it was accelerating downward at g, then there would be no pressure difference between F and G. But when it's accelerating downward faster than g, what that means is that the pressure at F is actually going to be higher than the pressure at g, because it's accelerating downward faster than gravitational acceleration. So Euler's equation is automatically going to take that into account. It's not like you need to subtract out g. It's already got the gravitational effect built in. So here's Euler's equation in the z direction. So what you're going to have to do is remind one another which is location 2, which is location 1, make the substitutions for elevation, for the pressure that's known, and then the pressure that's not known, it looks like is the pressure at F. So we know G. When you solve for the pressure at F, what you should expect to see is that it's actually higher than the pressure at G, because it's accelerating down faster than gravity. Okay, so that's a little bit of preliminary guidance there. I'm going to stop talking, turn you loose to work on this, and I'll be circulating around with the solution if you want to check your answers as you go.
There was 1 week where I gave.
Okay, I've got the solution on the screen to find the pressure at F. And remember that our convention is when we're thinking vertically, because to find the pressure at F, we have to consider this vertical acceleration. It's accelerating down at 12.5 meters per second squared. So if you're thinking vertically, then our notation, or our standard convention is that whatever's higher is location 2. So here, point F is location 2, and point G is location 1. And so when I substitute out F and G into Euler's equation, it's going to be the pressure at F plus gamma ZF minus the pressure at G minus gamma ZG. Now, our vertical datum can be any place, but just what makes sense to me is to say that the elevation of G is 0, so then the elevation of F is going to be 0.87 meters above it. So I'll give you a moment to look over this and compare it to what you did, or if you are still working on it, you can copy some things down, and then we'll move on to finding the unknown distance delta x. Okay, so we're comparing the pressure at F to the pressure at G. G is known. So look at the final result here. The pressure at F is the pressure at G, so 485,000, and then minus 115,731. So that minus here is because we're going up through the fluid. So the reason why the pressure is different at F compared to G partly is because it's higher in the fluid, so that's like the hydrostatic effect, but then there's also a pressure difference that it's accelerating downward, and that's where the second thing is, plus 147,465. So the pressure increases some because of the downward acceleration, it decreases some because of it being higher in the fluid elevation-wise, but the net difference between those two changes is because the acceleration is down faster than gravity, there's going to be more pressure at F than there is at G. So in the end, the pressure should be about 517 kilopascals at F. I'll again emphasize the importance of including the sign in the acceleration. This acceleration has both magnitude and direction, and if you fail to account for the correct sign, then that would have meant a decrease in pressure where we know it should be increasing. Okay, so that was how we found the pressure at F. Now to find the distance that's unknown, we're applying Euler's equation in the horizontal direction. So the acceleration is to the right at 15 meters per second squared. Location 2, which is further to the right, is H. Location 1, which is further to the left, is G. So if you substitute the G and the H subscripts into Euler's equation, you can see what we get here. And again, we've got a delta x is the distance now. Instead of being a delta z, the L direction is whatever direction the acceleration is. And so horizontally, if this is in the horizontal plane that we're working, because we know G and H are at the same elevation, then that's going to be some delta x distance between them, and the acceleration will be in x. And so we just cancel out the two elevations because H and Z are on the same elevation, so they're just removed from the expression on the left. So all we're left with is this change in pressure, and you can rearrange for the delta x and get that it's 1.79 meters. So inevitably, when I'm given a quiz or an exam with Euler's equation, some people will forget to put the sign with the acceleration. You know, they'll forget if it's down or to the left to put in the negative sign. Probably the next most common error is to switch which is 1 and which is 2, you know, forgetting that 2 is the further to the right if the acceleration is horizontal plane. 2 is the one that's above if it's in the vertical plane. And then another mistake that sometimes people make is they try and like combine the two accelerations together. Like here there was an acceleration in z and an acceleration in x, and sometimes they'll do like square this, add it together with square that, and take the square root, but there isn't like an average acceleration between the two directions. The only way to get the correct answer is just to break the acceleration up into the components and apply Euler's equation individually in the directions where there's acceleration, not combining the two together. Any questions before we move on from that example? Okay, now Euler's equation doesn't only predict changes in pressure. If the fluid is open to the atmosphere, it might be that the water surface is changing where it's located in response to the acceleration. So think about a tank of water that's open to the air, and before it was accelerated, it was just level. And now consider, what if you're holding onto a bucket of water and suddenly you accelerate that bucket of water to the right? Well, what you know, kind of just from experience, is that, you know, like if water's all the way up to the top of a glass, you have to move slowly or else it's going to spill. And the reason why is if you accelerate quickly, then the water's going to slosh out of the container in the opposite direction of the acceleration. So that's what this is showing. If it's accelerating to the right, then the fluid accumulates on the left side of the container. So this is actually very similar to what we've seen before with Euler's equation. Euler's equation predicts the change in piezometric pressure in response to some acceleration. And so what it's saying is the sum of the pressure plus gamma z is affected by this acceleration. And so what's happening when the container is open to the atmosphere is it's not just the pressure that's changing, but it's also the elevation that can change. So accelerate the tank to the right, and the fluid increases on the left side. Now, along the bottom of the tank, think about if it's this tank during the acceleration. The pressure is biggest on the left side because think about how much water is above it. It's only accelerating to the right. There's no separate vertical acceleration component. If it's accelerating to the right, then the pressure is going to be dependent on how much fluid is above a certain point. And so on the left side, there's more fluid above it, and so the pressure will be greater. One of the things that's interesting about Euler's equation is that the acceleration can be used to find out what this angle would be, the angle that the new fluid surface is going to make with respect to horizontal. And so the horizontal plane is when there's no lateral acceleration sideways, but when you do begin to accelerate it, then there's going to be a new angle that sets up. And so the tangent of that angle is the ratio of the acceleration in the horizontal direction with gravitational acceleration. And that is behind this other example that is on the back side of the in-class exercise that I gave you. So just to get a feel for how Euler's equation can be used to predict liquid level, what we're going to say is that this truck will never accelerate or decelerate more than 8.02 feet per second squared. So this truck is 18 feet long, has a 7-foot bed height, and we want to maximize how much water goes in there, but we don't want anything to slosh out. We don't want any liquid to spill. So what we're going to be trying to find out is when it's accelerating at 8.02 feet per second squared. The ratio of that acceleration to gravitational acceleration, which we know is 32.2 feet per second squared, will tell you the maximum angle that you can expect to see. And so once you've solved for that maximum angle, the question is, if the water is just right up to the edge of the 7-foot height, then what is that distance, and then what does it tell you about how deeply the tank can be filled? So this is a bit of a multi-step puzzle problem here, but what I'd like you to try and solve is based on, if it's accelerating forward, then the liquid level would accumulate on the back side. If it's slowing down, meaning to the left acceleration, then it would be sloshing the other way, where the water would be higher on the right than on the left. But either way, if we filled it all the way to 7 feet and it starts to accelerate, then the liquid's going to spill. So we want to find out how deeply can it be filled and still prevent spilling. Okay, so we know that we've got some triangle where, boy, that's not a very good triangle. Let me do better. Okay, we've got height h, 9 feet here, and there's going to be an angle that arises because of the acceleration. And the formula that Euler's gives us is that the tangent of the angle is the ratio of the acceleration. So 8.02 feet per second squared divided by 32.2 feet per second squared. And what that says is that the angle is 14 degrees. So that is this angle, 14 degrees. So we can calculate h by saying that the tangent of the angle is the opposite divided by the adjacent. So the definition of tangent is it's this opposite distance divided by the adjacent length distance. And what we don't know is the opposite. So the opposite is h. So in other words, h is going to be, well, let me rearrange it first this way. It's going to be the opposite is the adjacent multiplied by tangent of the angle. So 9 feet multiplied by the tangent of 14 degrees. And the tangent of 14 degrees is 0.2493. So this distance h, essentially h is the opposite, and so that is going to be 2.24 feet. Now the other way that you could get that distance is by recognizing similar triangles here, that the ratio of h to 9 is the same as the acceleration in the x direction relative to g. So what we're saying is that that deflection, the vertical deflection, is caused by the horizontal acceleration. And so how much h there is, the ratio of h to the horizontal distance 9 is the same as the acceleration to g. And so in other words, that means that h to 9 is the same as 8.02 to 32.2. So either way, we solve that h is 2.24 feet, and that means then that the maximum fill depth is going to be 7 feet minus that distance h. So fill depth maximum will be 7 minus 2.24, so that should be 4.76 feet. Anybody else get that same amount, that 4.76 feet? Yeah? Okay. Well, that's all we're going to do with Euler's equation for now. If you have any questions, please feel free to stop by during my office hours or send me an email and I'd be glad to help you out. Otherwise, I'll see you in class on Thursday.